Hello and welcome back to our plasma survey course. This is lecture 16. That means we're at least halfway, probably more. I never know how many lectures we're going to get to the end of the course. And that means we're going to start wrapping things up. Well, no, not quite, but we're going to start wrapping things up for inertial confinement fusion. We're going to talk about a few more things in this and I think the next lecture, and then we'll move to a different topic. Now, before we get into other issues, I wanted to mention one important concept that appears in often in ICF, and I'll explain one in a moment. That is Fermi degeneracy. You probably know from some other courses what that means. In non-expert terms, what we are concerned with is that when densities are very high and temperatures are relatively low, quantum mechanical effects can dominate the behavior of the electron gas. And I will not get into any expressions or equations. I hope you've heard of this before. If some energy is below a critical energy, that's called the Fermi energy or the Fermi temperature, then you have degeneracy, and you're not degenerate above that, and there is some sort of gray area or fuzzy area in between. Now, we in general want in ICF the electron gas to be as close as possible to be degenerate, if not really degenerate. And the reason is that, without again writing any equations, the pressure needed to obtain a given density can change easily by a factor of 2 or more, going from non-degenerate to a degenerate the other way. Well, it can change, depends which way. It's higher for a non-degenerate gas by about a factor of 2 and or more. And since pressure is, as we'll briefly discuss today at the end, money, how big your laser needs to be, we want to keep that pressure as low as possible. We want to be able to compress to very high densities our plasma, spending as little as possible. And that is the reason why, in general, the experiments will try to keep the electron gas to be Fermi degenerate. And in simple terms, that means that we should not preheat the electrons before they're compressed with the rest of the plasma. The physics and all of this is not simple. It's not trivial. So we'll not have the time to get into any of this and how you do it and what strategies you can use. But this is the general idea, the concept I wanted to mention, and that motivates the way, in part at least, the way laser pulses are modulated to obtain the best compression. Okay, now that's all I want to say about degeneracy. And now we can switch back to talk about ICF in picking up from where we left in lecture 50. Now, you may remember from the previous lecture that there were 4 phases in the ICF process. Sorry about that. And I'm going to cheat and let's see if I can make them appear magically all together. Yes, okay. So those were the interaction, compression, deceleration, and burn, where interaction is the interaction between laser or X-rays and your target, and then you compress the target starts slowing down when it gets dense enough, and then burns. So if you did really well, you can get ignition. We are completely going to skip the interaction part. We're going to focus on a little on the compression and deceleration. As I have already said, there are courses in departments that have strong emphasis on inertial confinement fusion that are only focusing on laser plasma interactions. That is the phase 1 of this system. We have little time to get into the details, but hopefully this will at least make you curious. Now, you may remember how we set up the system, but the easiest conceptually thing you could do in principle is to have a target that you're trying to implode, and this is not just my target, but it's completely homogeneous target with the correct spanning here. Sorry about that. That is, I'm not worrying about, or rather, I'm not designing my target to have any variations in any properties as a function of radius. And we're going to look at this target using, again, this is the simplest conceptually target. And we're going to look at it using the simplest approximation that you can think of, which I hope you will immediately guess, like the physicists always do. In this case, it's not the spherical cow. The spherical geometry is going to complicate things. And so we do the opposite. When physicists have a problem in complicated geometry, they make it a sphere. When they have a problem in a sphere, they make it a slab. We're difficult like that. Okay, then I'm going to assume that that is the shape of my system, and I'm just going to assume that I have a solid target and I'm trying to compress it. Now, here is what is going to happen. I'm going to have some surface where the energy is transferred to the plasma that forms outside the target. As soon as the laser hits the target surface starts being vaporized and forms a plasma, and immediately the laser cannot reach the target anymore, but it gives energy to the plasma, and then that energy is transferred to the fuel. I'm going to make my fuel blue, as in the picture above. I'm going to put some tags, and there is going to be a region which I can make, for instance, of this color, where other things happen. So let me put some words here to make this vaguely understandable. Here in the first little slab, I'm going to have energy deposition. This is somewhat, idealized. That's sort of where there is going to be a region. It's not just a surface. And here I'm going to have my solid target. Let me actually say this is going to be cold because it's not been heated by anything yet. And in that little region there, let me make a call out arrow here, is where I'm going to see ablation. Ablation means that the surface of the material heats up and explodes outward. And we'll see, hopefully shortly, why that matters. Okay, then what happens is that there is going to be pressure that's deposited by the energy that comes in. That's the first step. And where the laser or X-rays stop, this is the second step. This actually happens by thermal conduction. So maybe worth writing. I can make this a little bigger. I don't have this silly. No. Ah, okay, got it. Oops, and I cover my arrow. So that arrow indicates thermal conduction there. And the first arrow is my laser light or X-ray. Okay, this forms, as I said, compression wave that is a high pressure wave that moves radially. That is, I can do a plot in either pressure or density. Let's do it this way. density as a function of, let me call this x. I don't want to call it r, so we don't get confused. This direction is x. I have a compression wave. I'm not going to worry too much. I'm just going to make it this way. It's my compression wave. This is my initial state, rho naught and p naught. And here I have my compression wave coming in at rho 1 and p1. And this wave is going to travel to the right with a certain velocity. Let me call it v1. Or let me call it v sub s, because I will elaborate on that in a moment. Okay, now I don't want to put too many arrows here, so let me write what this is. And this is going to be my compression wave. Now, I've already mentioned equations that are called Rankine-Hugoniot conditions that prescribe relations between quantities on the two sides of this compression wave. And I should clarify that this compression wave is going to be a shock. There is quite a bit that you can do, and let me just write some results. Let's neglect the pressure before the shock arrives. Then you obtain that P1 is going to be equal to 2 over gamma plus 1 rho naught V sub S square. And rho 1 over rho naught is going to be equal to gamma plus 1 over gamma minus 1. These are pretty pretty standard the results for from gas dynamics. This is not quite plasma physics. And there is another relation for the value. Might as well write it just to confuse you a little more. Rho naught Vs squared, there should be a P0 here, but we are assuming that's 0, is equal to P1 plus rho 1 V1 squared, where V1 is the velocity of the fluid after the shock has passed. And I'm using that subscript S not to indicate just the shock, but to indicate the solid target. Okay, so that's what the S stands for. Okay, then this gives you value for the final pressure, and this is well known. It also tells you really you're not getting a lot of pressure, because the pressure after the shock is not that high. We'll see how it depends. Well, you see that it depends on the velocity of the shock, and more importantly, the density is not that high. You can only compress with respect to the initial density by something like a factor of 4, that you can easily get that from gamma equal 5/3. Okay, that was the simplest idea. Now we have our next option. We're going to use a more complicated target. We're going to put a foil on the surface of the target. That is, there is going to be a different material that stays that is around the target itself. In this case, we're using a slab model, so it's going to look something like this. Let's see. Here. Here I'm going to have my target as before, and let me use a different color. So that is going to be my foil, and this is going to be my target. And here I'm going to have pressure P1. Let me call this coordinate X again. That's not what ICF people do. It's always R, but well. This will be R equals 0. That's the center of the target. Now, if the pressure is constant, pressure P1, I suppose I could have written it. Assume Then we can obtain some special quantities. And it turns out that those quantities I'm going to write in a moment are going to depend on this thickness that we're going to call delta R. And to clarify, oil thickness is delta R, and target size is going to be R. Then the velocity, the implosion velocity, V sub F, where F stands for foil, this corresponds or contrasts to the V solid we had in the previous case, is going to be equal to this expression. And this is not difficult to derive, but you'll have to take my word for it. Or, well, not even my word. I'm getting this from a textbook. And I believe the result is correct. But I claim no responsibility. Okay, anyway, you see that the velocity increases when the foil is thin with respect to the target. That corresponds to what is called a high aspect ratio target. It's not the high aspect ratio of magnetic fusion. Ratio. Target gives larger velocity. Oops, I didn't make it fit. So let me. Where? We are going to define the aspect ratio as R over delta R. So we want this to be large. Indeed, if work this out, you find that V sub F V foil over V solid is equal to 8 over gamma plus 1 times R over delta R, everything under square root. That means that this high aspect ratio can give you an implosion velocity that's much higher if you have a foil instead of a thin foil, instead of having a solid target. And that is why that's how inertial confinement targets are made. There is something that we are not going to have time to go into really, but there is a very important warning here. That is that instabilities are going to constrain that aspect ratio. You cannot make it as large as you want. You need a minimum thickness to allow you to have an implosion that is not affected or not completely ruined, in the sense that it's not going to do what you wanted it to do by instabilities. Remember Rayleigh Taylor and Dirk Meyer-Meshkov. Now, the next thing we're going to look at is get a little bit deeper into the ablation phase. Well, actually, I should have called that the ablation process rather than the ablation phase. But let's talk a little bit about this process. And let me get a couple of lines in. Hoping that the noise that's coming from outside does not make it through the recording. Okay, we have, let's get back up here, light that comes and hits the surface. And energy is deposited, the surface of the foil blows out, and if you're paying attention, you will think, well, then there is going to be velocity. Let me redo this drawing for the foil. Of our material that comes out this way with velocity v sub a, which stands for ablation velocity. But that means that there is, as more and more mass flies to the left, there is momentum gained by my material. First, it was still not moving at all, then so the whole target starts moving, but there is a change in momentum. And if you're thinking of this in terms of Newton laws, that means there's going to be a force that pushes to the right, or you can think this as an action and reaction. Force, or if you prefer, a pressure that is pointing to the right. Or again, you can think this in terms of action and reaction. So if the surface blows one way, the rest of the material needs to be pushed in the opposite direction. And in fact, you're most likely more familiar than you may have yet realized with this process. This is what in ICF is very often called the rocket effect. This works exactly like a rocket. We don't always do it in intermediate mechanics. You've probably seen the equations solved in detail in maybe graduate level classical mechanics, but this is pretty straightforward stuff to calculate what's the force and how much thrust or how strong we're pushing the material in. And that is great because that's what we actually want to do. We want to compress the material. So the rocket effect is something that we want. So you can work out the details of the calculation. You'll remember that you're going to have a log of initial mass to final mass that appears in the velocity of the rocket as a function of time, and the velocity, well, let me just try the rocket, quote unquote, rocket equation. I don't know if that's an official name, but let me just try it. I'm sure you've seen it before. It's easy stuff, it's just rocket science. I'm sure you did not see that coming. My velocity in, that's going to be, let's do it in a different color. Sorry, I did not get my arrow ready. V sub I, that's velocity in, or velocity, implosion velocity, if you prefer. It's going to be equal to VA times the log of M0 over M. Or rather, people prefer, let me write it as it's normally done, just to make it a little more confusing. That's the properly defined is the expansion speed. And that's the one that's going to give me the implosion velocity. What happened to my log? Disappeared. Here, log of M0 over M. Sorry about that. And now I need to fix my figure here, because I just realized that we're talking about the expansion speed that I call this something else. I mixed names. This one is the expansion speed. Sorry about that. Where, in fact, with the ablation velocity, we mean something else, which is the velocity of the foil, with the velocity with which the foil moves. But without getting too bogged down in what happens with the different velocities and frames of reference, in fact, the expansion velocity is about the sound speed. And it's easy to calculate once we know the pressure. what is important is that as we're blowing off material from the surface of the target gets compressed, which is what we want. All right, so that is our velocity as a function of time for that's what the rocket equation gives you. And sorry, Kiram, I'm giving you the constant result. What is important for the compression is how much pressure is generated by this process. And here I'm going again to skip all the derivations. And just state a couple of results. Okay, let's see. There is a couple of ways to write this, just deciding which expression I want to give you. Well, let's see. I'm going to write two expressions, and I'm going to just say a few words about both. P, which is going to be megabar. Maybe I should type megabar. So I'll type it in a moment and give you the expression. It's equal to temperature 3 times temperature to 3.5, which is equal to 170. I'm going to first write it and then define the various symbols. Okay. P is my pressure, and as I said, but not right, it's going to be in megabar. Then T in this expression is I can put some brackets just to clarify that I'm talking about units here. P is going to be in units of, sorry, I didn't invent this. Hundreds of electron volts. Then what we have, E15, I'm sorry, I15 is the laser intensity or flux And that's in this expression is going to be in terms of in units. So make this work. 10 to the 15. And that's going to be watts over square centimeters. That's a pretty high intensity, in case you wonder. Okay, and now that I've done this, I've realized, well, I'll just type it. Oops. So that's one expression, and here is another one. P pressure is going to be approximately equal to 40 times I over lambda, and that's another favorite trick of the ICF communities to change units for expressions for the same thing in different circumstances. But lambda is the wavelength of the laser. Now I have two expressions. Because the first one is for indirect drive, and the second one is for direct drive. That is, they look different. And this gives also different expressions for the implosion velocity. Now, one more piece of information that is important here is, well, okay, so this process is actually helpful because we're making the capsule implode, but how much energy at the end does it actually get into the target? And that is quantified by standard way by defining a hydrodynamic efficiency. Where the hydrodynamic efficiency is defined as the ratio between the energy that gets used for the implosion and the energy that goes into the ablation process. So how much energy at the end does actually get into my target? And there are various expressions either in terms of masses or in terms of velocities. But what matters is that at the end, well, maybe I can write just one expression. So it's going to be equal to m divided by m0 times the log square of m over m0. And in a very idealized case, you can get to 70%. If you plot, let me clarify how you do this. I can actually try. Well, x is defined as m over m0. Remember, m0 is the initial mass. So this number is going to be less than 1. And if you set make that substitution, you'd find that the hydrodynamic efficiency is given by x log square x over 1 minus x. And you can plot this function and see that it has a maximum that is less than 1. As I said, this was all for a pretty idealized case. In reality, there is more that comes into play. The first issue is that the ablated material, it's not just moving with a certain velocity, but it's vaporized and it's acquiring thermal energy. It's heated by the laser. That is the ablating material, the one that's coming out of the rocket, the one that's pushing the actual target in, does not only contain kinetic energy, but also thermal energy. So that will decrease the efficiency, of course, because more energy needs to get or ends up in the ablated material. And in practice, in experiments, it's found that the hydrodynamic efficiency is of the order of 7 to 12%. So it's not terribly high. As we have already hinted at, the ICF process is quite inefficient in terms of transferring energy from the wall plug energy all the way to the fusion target. Now there is a little bit more that could be done. Let's see, in 5 minutes. Well, there is quite a bit more that could be done. I haven't really done anything. I've only given you results. But let me state another couple of results. It turns out that, well, you can calculate, of course, the implosion velocity from the ablation velocity. And this is not exact. It's an approximation of a more complicated expression. See if I got this right. Yes. That's for, let me just type it. This is for direct drive. Again, we want high aspect ratio. And in indirect drive, the implosion velocity you can express in different ways. Let me write it this way. It's going to be given by magic number beta to the 3/5 temperature in electron volts over 300. Sorry. To the power of 0.9. And okay, we got all the pieces. That's for indirect drive, assuming an aspect ratio of 30, which is a reasonable assumption. And T is the radiation temperature, and beta is a parameter that indicates the deviation from an ideal Fermi gas. So it tells you how far you are from full Fermi degeneracy. Okay, I'm not going to get into more details about the ablation phase. I'm only going to mention one thing to emphasize how interconnected and complicated the whole system is. The ablation process also has an effect on the development of instabilities in during the implosion. That means that the level of ablation is the ablation velocity is also going to tell you how thick or thin can you make the foil. So it's really pretty complex system. Okay, I think I'll stop here for today, and we'll pick it up from here in the next lecture. Thank you for your attention.